When we look at empty space, at the air in front of us, or the darkness between stars, we naturally assume there is nothing there at all. I remember the first time I encountered the idea that this assumption might be wrong, that emptiness itself might be a kind of fullness we simply cannot see. The thought seemed strange at first, almost like a riddle or a play on words, rather than a serious statement about how reality works. But physicists have spent nearly a century confirming that empty space is indeed filled with constant activity at scales too small for us to observe directly. The space in front of you right now, the seemingly empty air between your eyes and whatever surface lies ahead, contains energy and activity, even though nothing visible occupies that region. This is not a metaphor or a poetic way of describing something else. It's a measured fact of physics that experiments have confirmed over and over again. The vacuum of space, the emptiness that seems to be the definition of nothing at all, actually hums with quiet energy at the smallest scales that physics can describe. Every cubic centimeter of what we call empty space contains this hidden activity, whether that space exists in your room or in the vast darkness between galaxies. You are listening to The Drowsy Astronaut, and tonight we are exploring one of the strangest discoveries of modern physics, the realization that emptiness itself is more than it appears. There is no rush in what follows, only the gentle unfolding of an idea that changed how physicists understand the nature of space and reality. If you enjoy drifting off to real science explained calmly and warmly, consider liking this video or subscribing to join future journeys through these quiet wonders. The energy in empty space exists at scales almost impossibly small, in regions of space and intervals of time far beyond what our senses can perceive directly. We are talking about distances smaller than atoms, smaller than the particles that make up atoms, smaller than anything we have words for in everyday language. At these tiny scales, the rules that govern reality become strange in ways that took physicists decades to understand and accept. The emptiness that seems so simple and obvious to our daily experience turns out to be complicated and active when examined closely enough. The activity in empty space involves energy appearing and disappearing constantly, fluctuations that average out to nothing over longer times and larger scales, but are always present at the smallest levels. These fluctuations are not visible to any instrument we have built, not directly observable in any photograph or measurement we can take of the vacuum itself. Yet we know they exist because they affect things that we can measure, leaving subtle fingerprints on atoms and light and the forces between objects. The emptiness is shy about revealing itself directly, but generous in the clues it leaves behind. The discovery that empty space contains this hidden activity emerged from quantum mechanics, the branch of physics that describes how reality behaves at the smallest scales. Quantum mechanics revealed many surprising things about nature in the early 20th century, challenging intuitions that had seemed reliable for centuries of human observation. Among these surprises was the realization that energy could not simply be zero anywhere, that even the quietest possible state of empty space contained irreducible fluctuations. The mathematics demanded this, and eventually, experiments confirmed what the mathematics predicted. The concept can seem abstract when first encountered, a claim about reality that does not match anything we experience in our daily lives walking through rooms, or looking at the sky. We do not feel the energy of empty space pushing against us, do not see the fluctuations that supposedly fill every volume of what appears to be nothing at all. The hiddenness is real, a consequence of how small and brief the fluctuations are, existing at scales where our bodies and our instruments can only detect accumulated effects rather than individual events. The activity is always there, beneath the threshold of direct perception, a foundation layer of reality beneath everything visible. The implications of this discovery extend far beyond abstract physics, touching questions about the nature of space itself and what we mean when we say a region contains nothing. If empty space has energy, if the vacuum has properties and behaviors that can be measured and predicted, then perhaps emptiness is not the simple concept we assumed it to be. Perhaps what we call nothing is actually a special kind of something, the minimum state of a system that can never quite reach true zero. The questions become philosophical as well as physical, though the answers must ultimately come from experiment and observation. The energy of empty space exists everywhere that space exists, not just in laboratories or special conditions, but throughout the entire universe from beginning to end. The darkness between galaxies contains this energy. The space inside atoms contains this energy. The room where you sit or lie listening right now contains this energy, humming quietly beneath everything else. The universality is complete, a property of space itself, rather than something that occupies space the way matter occupies space. Wherever there is volume, wherever extension exists in any direction, the vacuum energy is present. The amount of energy in empty space becomes strange when physicists try to calculate it precisely, yielding numbers that are difficult to reconcile with what we observe about the universe. The calculations suggest enormous energy density, far more than we would expect from the gentle cosmos we observe expanding peacefully around us. This mismatch between calculation and observation represents one of the great puzzles of modern physics, a discrepancy that remains unsolved despite decades of effort. The energy is real, its effects are measurable, but its magnitude puzzles us deeply. The fluctuations in empty space take specific forms that physicists have learned to describe and predict, involving particles that appear briefly and disappear again almost instantly. These fleeting appearances are not the ordinary particles that make up atoms and light, but something stranger, something that exists only temporarily before vanishing back into the vacuum. The particles that flicker in empty space are called virtual particles, and their brief existence represents the activity that fills what we once thought was simply nothing at all. The vocabulary itself sounds like science fiction, yet describes measured reality. The vacuum of space continues its quiet activity, whether or not anyone observes it, whether or not any life exists to wonder about its nature. The fluctuations were happening before Earth formed, before the sun ignited, before the Milky Way assembled from scattered gas and dust. They continue now in every region of space we might choose to examine, and they will continue long after everything we know has changed beyond recognition. The emptiness has been full of activity for as long as emptiness has existed, which is to say, for as long as the universe has existed at all. The idea takes time to settle in, to become something more than words on a screen or sounds in the darkness, to become part of how we understand the space around us. I find myself sometimes looking at an empty corner of a room, and thinking about what fills it invisibly, the churning activity beneath the apparent stillness. The thought does not change what I see, but it changes what I know about what I see, adding a layer of reality beneath the surface that cannot be unseen. The emptiness looks the same, but I know it differently now. The journey into understanding what fills empty space begins with the particles themselves, the strange entities that flicker in and out of existence, faster than any instrument can directly observe. The activity in empty space takes the form of particles that appear and disappear constantly, emerging from nothing and returning to nothing in intervals so brief that direct observation is impossible. These particles are called virtual particles, a name that distinguishes them from the ordinary particles that make up matter and light, the particles that persist long enough to be measured directly. Virtual particles exist in pairs, a particle and its opposite appearing together, existing for the briefest moment, and then colliding and annihilating each other, leaving nothing behind. The process happens continuously, countless times per second, in every tiny region of space throughout the universe. The appearance of virtual particles is not a rare event that happens occasionally in special circumstances, but a constant background process, filling all of space at all times. The vacuum seethes with these appearances and disappearances, a continuous flickering of particles that average out to apparent emptiness over longer times and larger scales. Each appearance is independent, unpredictable in the details of exactly when and where it will occur, but predictable in the sense that some appearances will always be occurring somewhere. The mathematics that describes this process is well understood, tested by experiments, confirmed over decades of careful measurement and observation. The particles that flicker in empty space include every type of particle that physics has discovered, from the familiar electron to the stranger particles found in high-energy experiments and cosmic rays. Virtual electrons appear paired with virtual positrons, their antimatter counterparts, the two emerging together and annihilating each other, almost instantly. Virtual photons, the particles of light, flicker in and out constantly, pairs of them appearing and disappearing without ever being absorbed or detected by anything outside the vacuum itself. The vacuum contains the potential for every kind of particle, each type contributing its own fluctuations to the overall activity. The lifetime of a virtual particle is almost unimaginably brief, far shorter than any duration we have words for in ordinary language. A virtual particle might exist for less than a trillionth of a second, appearing and disappearing so quickly that no instrument could hope to catch it directly. The briefness is not a limitation of our technology, but a fundamental feature of how these particles exist, their lifetimes governed by the laws of quantum mechanics. The shorter the time a particle exists, the more energy it can borrow from the vacuum, a relationship we will explore more deeply soon. The visual appearance of this process, if somehow we could see it, would resemble a kind of effervescence, a constant bubbling of particles appearing and disappearing, like the surface of a carbonated drink. The comparison is imperfect because the bubbles in a drink persist for visible times and occupy measurable spaces, while virtual particles exist below any threshold we could directly perceive. But the sense of activity, of constant change beneath an apparently still surface, captures something true about what the vacuum contains. The stillness is an illusion created by our limited perception. the average of activity we cannot individually resolve. The pairs that appear always include both a particle and its antiparticle, the two emerging together with opposite properties that cancel when they meet. An electron has negative electric charge, so a positron has positive charge. And when they appear together and then collide, the charges cancel exactly. The conservation laws that govern physics are never violated, the borrowed properties always returning to zero when the particles annihilate each other. The universe is frugal in a sense, allowing temporary violations of emptiness only if they are paid back quickly enough that the overall account remains balanced. The concept of particles appearing from nothing and disappearing into nothing challenges the intuition we develop from everyday experience in the world of large objects and long durations. Objects in our daily lives persist, maintaining their existence from one moment to the next, changing only when something acts upon them from outside. Virtual particles violate this intuition, existing without cause in the ordinary sense, appearing simply because the laws of physics permit them to appear temporarily. The permission comes from quantum mechanics, which describes reality in terms of probabilities and possibilities, rather than the certainties of everyday experience. The energy required for a particle to exist comes from somewhere, and for virtual particles, that somewhere is the vacuum itself, a kind of loan that must be repaid quickly. The heavier a particle is, the more energy it requires, and the less time it can exist before the loan must be repaid through annihilation with its partner. Light particles, like electrons, can exist slightly longer than heavy particles like quarks, though all virtual particle lifetimes are incredibly brief by everyday standards. The relationship between energy and time is fundamental to why these particles can exist at all, a loophole in the laws of physics that nature exploits constantly. The detection of virtual particles cannot happen directly because they disappear too quickly to interact with any measuring device we could construct. Instead, we detect them through their effects on other things, the subtle ways they influence particles and fields that do persist long enough for measurement. A real electron, one that exists permanently until something happens to it, feels the presence of virtual particles around it, its properties slightly shifted by their constant flickering. These shifts can be measured, and when measured, they match the predictions of quantum mechanics precisely, confirming that the virtual particles are really there. The terminology can be confusing. The word virtual suggesting something less than real, something that does not quite exist in the full sense that ordinary matter exists. But virtual particles are real in the sense that matters for physics, which is to say, they have measurable effects on the world, effects that can only be explained by their existence. The word virtual distinguishes them from persistent particles, not to suggest they are imaginary or unreal, but to indicate their transient nature. They are real enough to affect experiments, real enough to require inclusion in calculations, real enough to change our understanding of emptiness. The vacuum filled with these flickering particles can be imagined as an ocean, not the familiar ocean of water, but a different kind of ocean underlying all of space. This ocean appears calm from a distance, smooth and featureless, the average of all its activity presenting the appearance of perfect stillness. But up close, at scales too small for distant observation, the ocean surface churns constantly, waves and ripples forming and collapsing, activity everywhere. We live at the scale where the ocean appears calm, but the activity continues beneath our threshold of perception, the foundation layer of reality beneath everything we can see. The flickering continues now, in the space around you, in the space between atoms in your body, in the space between stars in the sky, visible through whatever window you might see. The particles appear and disappear, whether or not anyone knows about them, whether or not any mind exists to contemplate their existence. They have been doing this for billions of years and will continue for billions more, the vacuum maintaining its constant activity as the universe expands and evolves around it. The existence of particles appearing from nothing and disappearing into nothing raises an obvious question about how such a thing could be permitted by the laws of physics. The laws of physics allow energy to appear from nothing, as long as that energy disappears again quickly enough. And this permission comes from one of the most fundamental principles of quantum mechanics. The principle is called the uncertainty principle, and it describes a fundamental limit on how precisely certain pairs of properties can be known at the same time. One version of this principle involves energy and time, stating that the more precisely you know when something happens, the less precisely you can know its energy, and vice versa. This trade-off creates the loophole that allows virtual particles to exist, energy appearing for intervals too brief to violate the broader conservation of energy. The uncertainty principle was introduced by Werner Heisenberg in 1927, part of the revolution in physics that created quantum mechanics and changed our understanding of nature at the smallest scales. The principle was not invented or designed, but discovered, emerging from the mathematics that described experimental results better than any previous theory had managed. Heisenberg and his colleagues found that nature itself imposed limits on what could be known, not because of any failure of instruments, but because of how reality worked at the fundamental level. The limits were built into the fabric of the universe, not obstacles to be overcome, but features to be understood. The relationship between energy and time in the uncertainty principle can be stated mathematically, but the essence is simple enough to describe in ordinary language. If a time interval is very short, then the energy during that interval can fluctuate widely without violating any law of physics. If a time interval is longer, the energy must be more precisely defined, fluctuations becoming more constrained as the duration increases. For intervals as brief as the existence of virtual particles, enormous energies can appear temporarily, enough to create particles with significant mass, before they annihilate and return their borrowed energy to the vacuum. The borrowing analogy captures something important about how this works. The energy appearing like a loan that must be repaid within a strict time limit. The larger the loan, the shorter the repayment period, nature allowing brief appearances of substantial energy while preventing those appearances from persisting indefinitely. The particles that flicker in the vacuum are living on borrowed energy, existing only as long as the uncertainty principle permits, disappearing when their allotted time runs out. The cosmic accounting always balances, the books closing with nothing owed or owing, emptiness restored after each brief fluctuation. The uncertainty principle applies not just to energy and time, but also to other pairs of properties, the most famous being position and momentum. The position-momentum uncertainty prevents us from knowing exactly where a particle is and exactly how fast it is moving at the same time. The energy-time uncertainty prevents us from knowing exactly when something happens and exactly how much energy it involves at the same time. These uncertainties are not about measurement limitations or imperfect instruments, but about the nature of reality itself, the fundamental graininess of existence at the smallest scales. The permission that the uncertainty principle grants for energy fluctuations is not optional or negotiable, not something that might or might not happen depending on circumstances. The fluctuations must happen, required by the mathematics that describes quantum systems, inevitable once the framework of quantum mechanics is accepted. The vacuum cannot be perfectly still, because perfect stillness would require perfect knowledge of the energy, which the uncertainty principle forbids. The activity in empty space is a consequence of fundamental physics, as certain as any other prediction that quantum mechanics makes. The timescales involved in these fluctuations are difficult to appreciate because they are so far removed from anything in human experience. We measure everyday durations in seconds, minutes, hours, periods long enough for us to perceive and respond to events around us. Virtual particle lifetimes are measured in tiny fractions of a second, numbers with dozens of zeros after the decimal point before any significant digit appears. The gap between human timescales and quantum timescales is enormous, comparable to the gap between the size of an atom and the size of the observable universe. The energy that appears during these fluctuations can be substantial by the standards of particle physics, enough to create electrons and positrons, enough to create quarks and antiquarks, enough, in principle, to create any particle that physics has discovered. The heavier the particle, the more energy required, and the shorter the time it can exist. But all possibilities occur somewhere, at some time. The vacuum tries out every option, creates every particle, explores every possibility permitted by the laws of physics, though always briefly, always returning to apparent emptiness. The mathematics that describes this process is part of quantum field theory, the framework physicists developed to combine quantum mechanics with the requirements of Einstein's relativity. Quantum field theory treats particles not as fundamental objects, but as excitations of underlying fields that fill all of space. The vacuum is the ground state of these fields, the quietest possible configuration. But the uncertainty principle prevents even the ground state from being perfectly quiet. The fluctuations in the fields are what we observe as virtual particles, brief excitations that disturb the quietness before it is restored. The acceptance of the uncertainty principle and its implications took time even among physicists. The ideas, challenging intuitions, built over centuries of classical physics that assumed determinism and precision. The old physics had suggested that with enough information, any future event could be predicted with perfect accuracy. That uncertainty was always a reflection of ignorance rather than a feature of reality. Quantum mechanics replaced this picture with something stranger, a reality where some things simply could not be known, where probability replaced certainty at the fundamental level. The uncertainty principle was central to this new understanding. The philosophical implications of uncertainty reach beyond physics into questions about knowledge and the nature of reality itself. If nature imposes fundamental limits on what can be known, what does this say about the universe we inhabit? The questions have occupied philosophers and physicists alike, generating debates that continue to this day about the interpretation of quantum mechanics. But whatever the philosophical conclusions, the practical reality of the uncertainty principle is confirmed by every experiment that tests it. The predictions, matching observations, with extraordinary precision. The uncertainty principle explains how vacuum fluctuations are possible. But explanation is not the same as proof. And proof requires experiments that detect the effects of these fluctuations on things we can actually measure. The existence of vacuum fluctuations was confirmed through experiments that measured forces where no forces should exist, pushes and pulls arising from emptiness itself, affecting real objects in measurable ways. The most famous of these experiments involved two metal plates placed very close together in a vacuum, with nothing visible between them to push or pull on either surface. Yet the plates experienced a force pushing them together, a gentle pressure arising not from any material but from the empty space surrounding them. This effect, predicted in 1948 and confirmed with precision in 1997, proved that vacuum fluctuations were real and could exert measurable forces. The physicist who predicted this effect was Hendrik Casimir, working at a research laboratory in the Netherlands on problems related to the forces between molecules. Casimir realized that if the vacuum contained fluctuating fields as quantum mechanics suggested, then the space between two close plates would be restricted in which fluctuations could fit. Certain wavelengths of fluctuation could not fit between closely spaced plates, while the space outside the plates had no such restriction. The imbalance would create a pressure difference, with more fluctuations pushing from outside than from the limited space between, resulting in a net force pressing the plates together. The prediction was elegant, but testing it proved difficult, because the force is extremely small and only becomes significant when the plates are extremely close together. The plates must be separated by less than a micrometer, less than the width of a human hair, for the Casimir force to become measurable with available technology. At such small separations, other forces like electrostatic attraction and surface contamination can easily overwhelm or mimic the vacuum effect. Decades passed before technology advanced enough to perform the measurement with sufficient precision to confirm Casimir's prediction. The definitive confirmation came in 1997, when Steve Lamoureux, working at the University of Washington, measured the Casimir force between a flat plate and a sphere using extremely sensitive instruments. The sphere geometry simplified some technical challenges of keeping flat plates perfectly parallel, while still testing the same underlying physics. The measured force matched the theoretical prediction within a few percent, confirming that vacuum fluctuations were real and behaved exactly as quantum mechanics predicted. The experiment transformed a theoretical idea into an established fact of physics. The Casimir effect demonstrates that emptiness can push on things, that the vacuum has physical properties that can be detected through careful measurement. The force is gentle, far too weak to notice in everyday life, but it is undeniably present when conditions allow its detection. Subsequent experiments have refined the measurements, improved the precision, explored different geometries and materials, all confirming the basic prediction that Casimir made decades earlier. The vacuum pushes, and we can measure how hard. The size of the Casimir force depends on the separation between the surfaces, growing stronger as the surfaces approach each other, according to a precise mathematical relationship. The force grows with the fourth power of the inverse separation, meaning that halving the distance increases the force by a factor of 16. This steep dependence on distance explains why the effect is so hard to detect at everyday scales, but becomes significant at microscopic separations. At the scale of nanometers, the Casimir force can become strong enough to stick microscopic components together, a phenomenon that engineers working on tiny devices must account for. The physical mechanism of the Casimir effect involves the difference between what fluctuations are permitted inside and outside the gap between the plates. The vacuum everywhere contains fluctuations of all possible wavelengths. But between close plates, only wavelengths that fit evenly can contribute. Long wavelengths that would span more than the gap simply cannot exist there, excluded by the geometry of the boundaries. Fewer fluctuations between the plates means less pressure from inside pushing outward, while the full range of fluctuations outside pushes inward, creating the net force. The explanation, in terms of virtual particles, pictures them appearing everywhere, but between the plates, only certain types can appear, those with wavelengths compatible with the narrow space. Outside the plates, all types can appear without restriction, creating more virtual particle pressure from outside than inside. The pressure difference is what pushes the plates together, emptiness from outside being more full than emptiness inside. The paradox is only apparent, resolved by recognizing that emptiness comes in degrees depending on what fluctuations are permitted. The Casimir effect has moved beyond being merely a confirmation of theory to becoming a practical consideration in modern technology. Engineers designing microscopic machines, devices with components separated by nanometers or micrometers, must account for Casimir forces in their calculations. The forces can cause parts to stick together unexpectedly, a phenomenon called stiction that can disable tiny devices if not properly managed. The vacuum that seemed like nothing has become a design consideration for the smallest machines humanity builds. The measurement of the Casimir effect has become increasingly precise over the years, since Lamoureux's groundbreaking experiment confirmed the basic prediction. Modern experiments measure the force with precision better than 1%, testing not just whether the effect exists, but whether its magnitude matches theoretical predictions in fine detail. The agreement between theory and experiment remains excellent, each improvement in measurement confirming again that quantum mechanics correctly describes the vacuum. The emptiness behaves exactly as the mathematics predicted it would. The philosophical significance of the Casimir effect extends beyond the technical physics, demonstrating that what appears to be nothing has properties and effects that are measurable. We tend to think of empty space as the absence of everything, the void between things that themselves have properties and existence. The Casimir effect shows that this intuition is wrong, that empty space itself has a nature that can be probed and understood. The nothing between things is itself a thing, or at least behaves like a thing in ways that affect other things around it. The confirmation of vacuum fluctuations through the Casimir effect raised questions about how much energy this activity represents, questions that led to one of the greatest puzzles in modern physics. The energy contained in empty space, even at the lowest possible temperature when all other energy has been removed, remains greater than zero, according to the laws of quantum mechanics. This remaining energy is called zero-point energy, named for the zero temperature at which it becomes the only energy remaining in a system. The uncertainty principle prevents any system from having exactly zero energy, because that would require perfect knowledge of both position and momentum, which the principle forbids. Every cubic centimeter of space contains this irreducible minimum energy, a baseline that cannot be removed by any physical process. The zero-point energy of a single quantum system is small, barely worth mentioning for most practical calculations, a tiny vibration that persists when all other motion has stopped. But empty space contains infinitely many possible modes of vibration, infinitely many ways the quantum fields can fluctuate. And summing over all these modes produces numbers that seem impossibly large. The calculations suggest that every cubic meter of space contains enormous energy, far more than the energy of all the matter in the observable universe, concentrated into that same volume. The numbers are so large that they initially seem like mistakes, errors in the mathematics, rather than predictions about reality. The discrepancy between the calculated energy and what we observe about the universe represents one of the most significant unsolved problems in physics. If empty space truly contained the energy that naive calculations suggest, the gravitational effects would be overwhelming, curving space so dramatically that the universe we observe could not exist. Stars, galaxies, and the gentle expansion of the cosmos would be impossible if vacuum energy had the magnitude that straightforward calculation predicts. Yet we exist. The universe expands gently, and something must be wrong with the naive picture. The resolution of this puzzle remains unknown, the subject of ongoing research and theoretical speculation that has not yet produced a satisfying answer. Some physicists suggest that unknown mechanisms cause most of the calculated energy to cancel, leaving only a tiny residue that matches observation. Others propose that our understanding of quantum gravity, the combination of quantum mechanics with general relativity, is incomplete in ways that will eventually resolve the discrepancy. The puzzle has earned the name the cosmological constant problem, and it remains among the most important open questions in fundamental physics. The energy that calculations predict would have specific gravitational effects if it existed at the calculated magnitude, curving space and accelerating the expansion of the universe in ways that depend on its precise value. Observations of the universe's expansion, particularly measurements of distant supernovae and the cosmic microwave background, reveal that space does have a small energy density that accelerates expansion. This energy, called dark energy, is real and measured, but is roughly 120 orders of magnitude smaller than what naive calculations predict. The gap between prediction and observation is the largest numerical discrepancy in all of physics. The existence of zero-point energy is not itself controversial, confirmed through experiments like the Casimir effect and the Lamb shift that we will explore later. What remains controversial is how much energy exists and why its gravitational effects are so much smaller than calculation suggests. The energy is there, it has effects, but it does not behave as naively expected when it comes to curving space and influencing the cosmic expansion. Understanding why remains one of the great goals of theoretical physics. The concept of zero-point energy emerges naturally from the mathematics of quantum mechanics, appearing whenever the equations are applied to any system, from atoms to fields, filling all of space. A simple harmonic oscillator, like a weight on a spring, has zero-point energy in quantum mechanics even when cooled to absolute zero. The oscillator cannot be perfectly still, because perfect stillness would violate the uncertainty principle, so it retains a minimum vibration even at zero temperature. The same logic applied to the quantum fields that fill space. produces the vacuum energy that fills what we call empty space. The zero-point vibration of quantum systems has been observed directly in experiments where oscillators are cooled to near absolute zero, and their remaining motion is measured. The motion persists, matching quantum mechanical predictions, confirming that the zero-point energy is real and not merely a theoretical artifact. The energy cannot be extracted for useful work under ordinary circumstances, but it is present, contributing to the physical properties of the systems that contain it. The emptiest state still contains this irreducible activity. The question of whether zero-point energy could be extracted for practical purposes has generated considerable interest and considerable nonsense over the years since its discovery. The energy is real, but the laws of thermodynamics prevent us from extracting it for useful work through any conventional means. The vacuum is already at its lowest energy state, with no lower state to fall into while releasing energy for capture. Proposals to tap vacuum energy for unlimited power generation typically misunderstand either the physics or the meaning of zero-point energy as the minimum rather than a surplus. The energy of empty space, whatever its true magnitude, contributes to the properties of particles and forces in ways that calculations must include to match experimental observations. The electron has a magnetic moment, a quantity that can be measured with extraordinary precision, and the measured value differs slightly from what a simple calculation, without vacuum corrections, would predict. Including the effects of virtual particles and vacuum fluctuations brings the calculation into agreement with measurement, confirming that the vacuum corrections are real. The energy of emptiness affects the properties of matter in measurable ways. The puzzle of vacuum energy connects to the deepest questions about the nature of reality and the relationship between quantum mechanics and gravity. General relativity, Einstein's theory of gravity, says that energy curves space, all energy without exception, including whatever energy empty space contains. Quantum mechanics, the theory that predicts vacuum energy, says that energy cannot be zero even in the emptiest state. The two theories seem to make incompatible predictions when applied to the vacuum, and resolving this incompatibility may require new physics that we have not yet discovered. The discovery that empty space contains energy emerged from the development of quantum mechanics, a history that reveals how strange ideas became accepted physics through careful thought and experimental confirmation. The idea that empty space might contain energy emerged gradually through the early 20th century, as physicists developed the theory of quantum mechanics to explain phenomena that classical physics could not describe. The old physics, built over centuries from the work of Newton and Maxwell and many others, assumed that space was a passive background, a container for matter and energy that had no properties of its own. The new physics would reveal that this assumption was wrong, that space itself participated in physical processes in ways the old theories had not anticipated. The discovery took decades and required contributions from many minds working on different aspects of the puzzle. The uncertainty principle, introduced by Werner Heisenberg in 1927, was an early hint that the vacuum could not be perfectly empty and still. Heisenberg showed that certain pairs of properties could not both be precisely defined at the same time, a fundamental limit imposed by nature rather than by the imperfection of measuring instruments. Applied to the question of vacuum energy, the uncertainty principle suggested that perfect emptiness, with exactly zero energy, was impossible because it would require perfect precision in properties that nature forbade from being simultaneously determined. The emptiness had to contain some activity, some minimum fluctuation that could not be eliminated. Paul Dirac's work on combining quantum mechanics with special relativity in the late 1920s provided another crucial piece of the puzzle. Dirac developed equations describing how electrons behaved when moving at high speeds, and these equations seemed to predict the existence of particles with negative energy, a concept that made no physical sense. Dirac reinterpreted these solutions as representing antimatter, particles with opposite properties to ordinary matter, and predicted that empty space might contain a sea of such particles whose interactions produced observable effects. The picture was later refined, but Dirac's work established that the vacuum was not simple emptiness, but had structure and properties. The development of quantum field theory through the 1930s and 1940s transformed understanding of both particles and empty space, providing the mathematical framework that made vacuum energy a calculable quantity. Quantum field theory describes particles as excitations of underlying fields that fill all of space, with the vacuum representing the ground state of these fields. The ground state could not have zero energy because of the uncertainty principle, so the vacuum contained 0-point energy from every field the theory included. The framework made vacuum energy not just a philosophical possibility, but a mathematical necessity. The prediction of the Casimir effect in 1948 provided a concrete way to test whether vacuum energy was real or merely a theoretical artifact. Hendrik Casimir showed that the energy between two metal plates should differ from the energy outside them, creating a measurable force that would confirm the reality of vacuum fluctuations. The prediction was elegant, arising directly from quantum theory without additional assumptions, providing a clear target for experimental confirmation. Though decades would pass before technology allowed precise measurement, the theoretical foundation was solid. The Lamb shift, discovered experimentally in 1947, provided early evidence that vacuum fluctuations affected real particles in measurable ways. Willis Lamb and Robert Rutherford measured a tiny difference between energy levels in hydrogen atoms that classical theory and simple quantum mechanics could not explain. The difference arose from the interaction between the electron and the virtual particle surrounding it, vacuum fluctuations, shifting the electron's energy by a small but measurable amount. The agreement between theory and experiment confirmed that vacuum effects were real and that the calculations describing them were correct. The theoretical understanding of how to calculate vacuum effects developed through the work of Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the late 1940s. These physicists developed methods for handling the infinities that appeared in naive calculations, techniques called renormalization that allowed precise predictions to be extracted from the mathematics. The predictions matched experiments to extraordinary precision, confirming that quantum electrodynamics, the theory of light and electrons, including vacuum effects, correctly described nature. The theoretical framework was complete, at least for electromagnetic interactions. The acceptance of vacuum energy as a real physical phenomenon rather than a mathematical artifact took time, with some physicists remaining skeptical even as experimental evidence accumulated. The concept seemed to violate common sense, to claim that nothing contained something, that emptiness was a kind of fullness. But common sense is built from everyday experience, and everyday experience does not include the scales at which vacuum effects become significant. The physics proceeded despite philosophical discomfort, following the evidence rather than intuition. The confirmation of the Casimir effect in 1997 marked a kind of closure to the historical development, demonstrating that vacuum forces were real and measurable with modern technology. The decades between prediction and precise confirmation reflected the difficulty of the measurement, rather than any doubt about the theory, which had been confirmed indirectly through many other experiments. The direct measurement satisfied any remaining skepticism, transforming vacuum energy from a theoretical inference to an observed phenomenon. The history shows how science proceeds when encountering ideas that challenge established understanding. Through mathematical development, theoretical prediction, and experimental confirmation. The strangeness of the ideas did not prevent their acceptance once the evidence became sufficient, though it did generate discussion and debate along the way. Quantum mechanics changed our understanding of reality at the smallest scales, and vacuum energy was part of that change, a consequence of the new theory that could not be avoided once the theory was accepted. The framework that emerged from this historical development, quantum field theory, provides the foundation for understanding how vacuum fluctuations arise from the underlying structure of reality. The modern understanding of vacuum fluctuations emerges from quantum field theory, a framework that describes the universe not in terms of particles, but in terms of fields that fill all of space and give rise to particles through their excitations. Every type of particle corresponds to a field, an invisible entity extending throughout the universe that can be calm or excited, quiet or active. The electron corresponds to the electron field, the photon to the electromagnetic field, quarks to their respective fields, and so on through all the particles that physics has discovered. The fields are the fundamental reality, and particles are what we observe when the fields become excited. A field can be imagined as something like a fabric stretched through all of space, capable of rippling and vibrating in various ways. A calm, unexcited field lies flat, containing no particles, representing the closest thing to emptiness that physics describes. An excited field contains ripples, and these ripples are what we observe as particles, traveling through space as disturbances in the underlying field. The particle picture and the field picture are both valid, but the field picture makes vacuum fluctuations easier to understand as inevitable consequences of quantum mechanics applied to fields. The vacuum state in quantum field theory is defined as the state with no particles, the quietest possible configuration of all the fields filling the universe. This state is not empty in the sense of containing nothing at all, but empty in the sense of containing no excitations, no ripples, no particles. The fields themselves remain, stretched through all of space, awaiting excitation, but currently calm. This vacuum state is the baseline from which all other states are measured, the reference point for defining what it means for particles to exist. The uncertainty principle prevents the fields from being perfectly calm even in the vacuum state, requiring them to retain minimum fluctuations that cannot be eliminated by any process. A perfectly calm field would have both its amplitude and its rate of change precisely defined, violating the uncertainty principle that forbids such precise simultaneous definition. The fields must fluctuate slightly, must retain some activity even in their ground state, and these irreducible fluctuations are what we call vacuum fluctuations. The mathematics demands this, and experiments confirm it. The fluctuations in the fields are what give rise to virtual particles, the brief excitations that appear and disappear throughout the vacuum. A fluctuation in the electron field appears briefly as a virtual electron and virtual positron before collapsing back to the ground state. A fluctuation in the electromagnetic field appears as a virtual photon pair before similarly dissolving. The vocabulary of particles and the vocabulary of field fluctuations describe the same underlying reality from different perspectives, both valid and both useful for different purposes. Each type of field contributes its own fluctuations to the overall activity of the vacuum, layering multiple types of activity throughout every region of space. The electromagnetic field fluctuates, the electron field fluctuates, the quark fields fluctuate, and all the other fields known to physics contribute their own vibrations. The vacuum is not calm in one sense and active in another, but calm only in the average sense, active in detail with contributions from all the fields simultaneously. The apparent emptiness conceals a rich structure of overlapping fluctuations. The energy of the vacuum comes from these fluctuations, the zero-point energy of every field mode summed over all the modes that exist throughout space. Each mode contributes a small energy, but the number of modes is infinite in any straightforward counting, leading to the enormous energies that calculations naively predict. The puzzle of why this energy does not have overwhelming gravitational effects remains unsolved, but the framework that produces the prediction is well established and confirmed through other experiments. The mathematics works even when its implications seem to conflict with observation. The visual picture of fields filling space, fluctuating constantly, giving rise to fleeting particle appearances, helps make the abstract mathematics more intuitive. The vacuum is not passive emptiness, but active substrate, the foundation layer of reality beneath everything else we observe. Particles come and go, matter moves and interacts, but the fields persist, filling space whether or not anything excites them, fluctuating whether or not anyone observes them. The fields are always there, the stage on which everything else happens. The quantum field theory framework unifies the description of particles and forces, explaining how they interact through the exchange of field excitations between sources. When two electrons repel each other, the explanation involves the electromagnetic field fluctuating between them, virtual photons carrying the force from one electron to the other. The vacuum fluctuations are part of this picture, virtual particles mediating interactions throughout space, even between particles that never come close enough to touch directly. Forces themselves emerge from the activity of the vacuum. The standard model of particle physics, our most complete theory of fundamental particles and forces, is built entirely on the quantum field theory framework. The model describes all known particles as excitations of their corresponding fields, all known forces as mediated by the exchange of force-carrying particles that are also field excitations. The vacuum in the standard model is not empty, but filled with the ground states of all these fields, fluctuating constantly as the uncertainty principle requires. The model has been tested to extraordinary precision, confirming the framework that places vacuum fluctuations at the heart of physical reality. The quantum field picture makes the vacuum seem less strange, not a violation of the principle that nothing comes from nothing, but a realization that what we call nothing is itself something. The fields exist even when no particles exist. The substrate persists even when no excitations disturb it. The vacuum is the minimum state of this underlying reality, not the absence of reality, just the absence of excitations above the irreducible minimum. Understanding the fields helps us understand why emptiness cannot be truly empty. The effects of vacuum fluctuations extend beyond the Casimir force, influencing atoms and light in subtle but measurable ways. The electrons in atoms do not exist in isolation, but are surrounded by vacuum fluctuations that constantly interact with them, affecting their properties in ways that can be measured with extraordinary precision. These effects were first detected in hydrogen, the simplest atom, where tiny discrepancies between theory and experiment pointed to influences that older theories could not explain. The Lamb shift, discovered in 1947, revealed that vacuum fluctuations changed the energy levels of electrons in measurable ways, confirming that the fluctuations were real and could not be ignored. The effects are small but undeniable, part of the evidence that convinced physicists that empty space was not simply empty. The Lamb shift was discovered by Willis Lamb and Robert Rutherford using microwave techniques to measure energy levels in hydrogen atoms with unprecedented precision. According to earlier quantum theory, two particular energy levels in hydrogen should have had exactly the same energy, a degeneracy arising from the symmetry of the electron's motion. Lamb and Rutherford found that these levels were slightly different, separated by a tiny amount that the old theory could not explain. The discrepancy was small, less than 1 part in a million of the total energy, but it was real and demanded explanation. The explanation came from the interaction between the electron and the virtual particles that constantly appeared and disappeared in the space around it. The electron is never truly alone, but always surrounded by a cloud of virtual photons and virtual electron-positron pairs that affect its properties through their brief interactions. These interactions shift the electron's energy slightly, raising one of the supposedly degenerate levels relative to the other and producing the effect that Lamb and Rutherford measured. The agreement between theoretical prediction and experimental measurement confirmed that vacuum fluctuations had to be included to describe atoms correctly. The calculation of the Lamb shift required the new techniques of quantum electrodynamics, the theory of light and electrons that physicists developed in the late 1940s to handle the infinities that appeared in naive vacuum calculations. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga independently developed methods for extracting finite, meaningful predictions from calculations that initially gave infinite answers. Applied to the Lamb shift, their methods gave predictions that matched experiment to several decimal places, confirming both the theory and the reality of the vacuum effects it described. The electron's magnetic moment provides another example of vacuum effects that can be measured and calculated with remarkable precision. An electron behaves like a tiny magnet, and the strength of this magnetism can be measured through its interactions with magnetic fields. Simple theory predicts a certain value, but the measured value differs slightly by about 1 part in 1,000 due to interactions with virtual particles. The agreement between the calculated correction and the measured discrepancy is one of the most precise confirmations in all of physics, theory and experiment, matching to more than 10 decimal places. The precision of these measurements and calculations represents one of the greatest achievements of 20th century physics, a triumph of both experimental technique and theoretical understanding. The electron magnetic moment is known to parts per trillion, and the theoretical calculation, including vacuum effects, matches this precision almost perfectly. Such agreement is not coincidence but confirmation, demonstrating that the framework of quantum electrodynamics correctly describes reality at the most fundamental level currently accessible. The vacuum fluctuations are as real as the electrons they affect. The effects on atoms extend beyond energy levels to include the lifetimes of excited states, the rates at which atoms emit light, and various other properties that can be measured and calculated. In every case, including vacuum effects, improves the agreement between theory and experiment, confirming that the fluctuations must be included for accurate predictions. The vacuum is not a passive background, but an active participant in atomic physics, influencing everything that happens at the atomic scale through constant interaction with real particles. Light itself is affected by passage through the vacuum, its properties subtly changed by interactions with the virtual particles it encounters along its path. The vacuum has a kind of polarizability, responding to light in ways that affect the light's propagation, even through apparently empty space. These effects are extremely small and difficult to measure, but they are predicted by theory and provide additional confirmation of the vacuum's active nature. The emptiness responds to light, though gently. The interactions between real particles and virtual particles create a kind of fuzziness around every electron, proton, and other particle, a cloud of vacuum activity that influences how the particle appears from outside. An electron's charge and mass, as measured from a distance, differ slightly from what they would be if the electron existed in true emptiness, without vacuum fluctuations. This difference, called renormalization in the technical literature, is part of what makes the theory work. The observed properties emerging from a combination of bare properties and vacuum corrections. The experimental confirmation of vacuum effects on atoms came at a crucial time in the development of physics, when the new theories of quantum electrodynamics were still establishing their credibility. The Lamb shift provided a quantitative test that the theory passed brilliantly, building confidence that the mathematical framework correctly described physical reality. Without experimental confirmation, the theory might have remained an elegant mathematical structure, without grounding in observed facts. The measurements grounded the theory in reality. The precision achieved in measuring and calculating vacuum effects continues to improve with advances in technology and theoretical understanding. Modern experiments measure atomic properties to ever more decimal places, and theoretical calculations keep pace, including ever more subtle vacuum corrections. The agreement remains excellent, confirming again and again that the vacuum is active, influential, and correctly described by the theoretical framework that physicists have developed. The fluctuations that fill empty space affect atoms in exactly the ways the mathematics predicts. The implications of vacuum energy extend beyond atoms and experiments to the largest scales in cosmology, where the energy of empty space may connect to the mysterious dark energy accelerating the expansion of the universe. The discovery in 1998 that the universe's expansion is accelerating came as a surprise to cosmologists, who expected gravity to be slowing the expansion down over time. Observations of distant supernovae revealed that they were fainter than expected, indicating that they were farther away than a decelerating universe would place them. The implication was clear. Something was pushing the universe apart, accelerating the expansion, rather than allowing it to coast or slow down. This something was given the name dark energy, a label that acknowledges our ignorance about its true nature. Dark energy behaves like energy inherent in space itself, a property of emptiness that increases as space expands and more emptiness comes into existence. The more space there is, the more dark energy exists, creating a runaway effect that accelerates the expansion over cosmic time. This behavior resembles exactly what vacuum energy should produce if it had gravitational effects, suggesting a natural connection between quantum mechanics and cosmology. The vacuum energy predicted by physics and the dark energy observed by astronomers might be the same thing seen from different perspectives. The connection seems compelling until the numbers are compared, at which point one of the largest discrepancies in all of physics becomes apparent. The vacuum energy calculated from quantum field theory is roughly 120 orders of magnitude larger than the dark energy observed through cosmological measurements. 120 orders of magnitude means a factor of 1, followed by 120 zeros. A gap so enormous that it suggests something is deeply wrong with either the calculation or our understanding of how vacuum energy gravitates. No known mechanism can explain such a massive cancellation. The cosmological constant problem, as this discrepancy is called, has resisted solution for decades, despite intense effort from theoretical physicists around the world. Various explanations have been proposed, from unknown symmetries that cancel most of the vacuum energy to the idea that we simply do not understand how quantum mechanics and gravity combine. None of these proposals has achieved widespread acceptance, leaving the problem open and the connection between vacuum energy and dark energy uncertain. The puzzle remains one of the deepest in fundamental physics. The observation that the universe contains dark energy amounting to roughly 68% of its total energy content came from multiple independent measurements that all pointed to the same conclusion. The cosmic microwave background radiation, the afterglow of the early universe, showed patterns consistent with a universe containing dark energy. The distribution of galaxies and galaxy clusters confirmed the same picture. The evidence is overwhelming that something like dark energy exists, even if its precise nature remains mysterious. If vacuum energy is responsible for the cosmic acceleration, then the quantum fluctuations filling empty space have consequences that extend across the entire universe. The same phenomenon that produces the Casimir force between close metal plates would be responsible for pushing galaxies apart on scales of billions of light years. The connection between laboratory physics and cosmology would be complete, the smallest scales influencing the largest through the energy of empty space. The poetry of this connection appeals even when the discrepant numbers frustrate explanation. Alternative explanations for dark energy exist, including modifications to gravity that would mimic the effects of vacuum energy without actually invoking it. Some physicists suggest that general relativity, Einstein's theory of gravity, might be incomplete on cosmic scales, behaving differently than expected in ways that produce accelerated expansion. These alternatives are difficult to test and have their own theoretical challenges, but they remain possibilities while the vacuum energy explanation faces its numerical difficulties. The anthropic approach to the cosmological constant problem suggests that the vacuum energy might vary across different regions of a vast multiverse, with our universe having a value small enough to allow galaxies and life to exist. In regions where vacuum energy is larger, the expansion would be so rapid that matter would never clump into galaxies, and life would never emerge. We observe a small vacuum energy because only small vacuum energy allows observers to exist. The reasoning is controversial, but difficult to dismiss entirely. The vacuum energy that drives cosmic acceleration, whatever its precise origin, shapes the ultimate fate of the universe across timescales far exceeding the current age of the cosmos. If dark energy continues to push, the expansion will accelerate forever, eventually carrying galaxies beyond each other's horizons, leaving each galaxy isolated in an increasingly empty cosmos. The energy of emptiness, if that is what drives the acceleration, determines the ultimate loneliness of the universe, the final state toward which all of cosmic evolution points. The connection between quantum mechanics and cosmology through vacuum energy remains tantalizing but incomplete. A suggestion of deep unity between the smallest and largest scales that we have not yet fully understood. The mathematics seems to demand a connection, but the numbers refuse to cooperate, leaving physicists puzzled about what is missing from their understanding. Progress will come, perhaps, from new theoretical insights or new observations that reveal aspects of reality currently hidden. The connection awaits completion. The observation of dark energy transformed our understanding of the cosmos, revealing that emptiness plays an active role in cosmic evolution. Whether this emptiness is the same vacuum energy predicted by quantum mechanics or something else entirely remains one of the great questions facing physics. The answer, when it comes, will illuminate both the nature of empty space and the fate of the universe that space contains. The strange properties of the quantum vacuum raise philosophical questions about the nature of emptiness and what we mean when we say a region contains nothing at all. The discovery that empty space contains energy and activity challenges the intuitive understanding of nothingness that most people carry from everyday experience into their thinking about physics and reality. When we clear a room of objects, we think of the room as empty, as containing nothing where once there was something. When we think of outer space, the vast darkness between stars and galaxies, we imagine the ultimate emptiness, a void stretching through unimaginable distances. The physics of vacuum fluctuations suggests that both intuitions are wrong, that even the emptiest emptiness contains activity we simply cannot see directly. The question of what nothing truly means becomes complicated when physics reveals that the most nothing-like state we can achieve still contains something. We can remove all matter from a region, evacuate all gas, exclude all light, cool to absolute zero where all thermal motion stops, and still the vacuum fluctuations continue. We cannot remove them because they are not added to space from outside, but are intrinsic to space itself, properties of the vacuum rather than contents of the vacuum. The emptiest possible state is not empty in any absolute sense. The distinction between different kinds of nothing becomes important when thinking carefully about what physics describes. We might distinguish between practical nothing, the absence of anything we would normally notice, and absolute nothing, the absence of everything, including the properties of space itself. Practical nothing is achievable. We can create near-perfect vacuums in laboratories, and nature achieves excellent vacuums between galaxies. Absolute nothing may be impossible. A concept that refers to something that cannot exist in the universe, as physics describes it. Space itself has properties in quantum field theory, characterized by the fields that fill it and the vacuum states of those fields. The electromagnetic field extends through space, whether or not any light exists to excite it. The electron field extends through space, whether or not any electrons exist as its excitations. These fields are not nothing. They are mathematical structures that describe real properties of physical reality. The vacuum is the ground state of these fields, not their absence. Removing the fields entirely would mean removing space itself. The philosophical question of why there is something rather than nothing takes on new dimensions when we realize that what we called nothing is actually something after all. The question might better be phrased as why there is this rather than that, why the vacuum has the particular properties it has rather than different properties. The ground state energy could, in principle, have been different. The fluctuations could have had different characteristics. The fields could have been arranged differently. Why things are as they are rather than some other way remains a deep question. The impossibility of creating true emptiness reflects the nature of quantum mechanics, the uncertainty principle forbidding the perfect stillness that true emptiness would require. A region of absolutely nothing would have perfectly defined values for all properties. Zero energy, zero field amplitude, zero everything. But the uncertainty principle forbids such perfectly defined states, requiring fluctuations in properties that cannot simultaneously take precise values. The prohibition is mathematical, but its consequences are physical. True emptiness cannot exist. The vacuum, as physics describes it, might be imagined as a kind of plenum rather than a void, a space full of potential rather than empty of everything. The potential for particles exists throughout the vacuum, the possibility of excitation present everywhere, even when no actual excitations currently disturb the ground state. The distinction between potential and actual becomes important. The vacuum contains potential particles without containing actual particles. Possibility without actuality. The emptiness is pregnant with possibility. Some philosophers have suggested that the vacuum of quantum field theory should not be called nothing because it still contains structure, fields, properties, and energy. True, nothing would have no properties, no characteristics, no existence of any kind, and such a state may simply be impossible or even incoherent as a concept. The vacuum is the closest physics comes to nothing, but physics does not claim that the vacuum is nothing. In an absolute sense, the modesty of the claim is important for avoiding confusion. The question of whether absolute nothing could exist may be unanswerable because we cannot observe or describe what has no properties to observe or describe. We can only study what exists, and the vacuum exists, and it has the properties that physics describes. What lies beyond what exists, if anything, lies beyond what physics can address. The questions become philosophical, moving out of science and into metaphysics, where evidence cannot settle debates. The shift in understanding from empty space as passive container to active participant in physical processes changes how we might think about the universe at a deep level. The universe is not matter floating in emptiness, but matter embedded in a substrate that has its own properties and its own physics. The stage on which the drama of the cosmos plays out is itself part of the drama, influencing events rather than merely providing a location for them. Space participates in what happens within it. The recognition that empty space is not truly empty invites a kind of humility about the relationship between everyday intuition and physical reality. What seems obvious from daily experience, that empty means empty, turns out to be wrong when examined at scales where quantum effects become important. The universe does not conform to expectations built from human-scale experience. And learning this is part of what physics offers to those who study it. The lessons extend beyond specific facts to a more general appreciation of how strange reality can be. The philosophical implications of vacuum fluctuations continue to be debated by physicists and philosophers interested in the foundations of physics and the nature of reality. The discussions cover not just what the vacuum is, but what existence means, what reality contains, and how we should think about the relationship between physics and metaphysics. These are deep questions that physics touches without fully answering, inviting continued thought and investigation. Despite decades of study, fundamental questions about the vacuum remain unanswered, mysteries that continue to occupy physicists working at the frontiers of current understanding. The cosmological constant problem remains unsolved after decades of effort. The enormous discrepancy between calculated vacuum energy and observed cosmic acceleration standing as one of the greatest puzzles in all of physics. The calculations seem sound, based on well-tested principles of quantum field theory, yet their results conflict dramatically with observations of the universe around us. Some unknown mechanism must cancel most of the calculated energy, reduce its gravitational effects, or modify how we understand the relationship between vacuum energy and gravity. Finding this mechanism remains an active goal of theoretical physics. The problem has resisted many proposed solutions, each one running into difficulties that prevent widespread acceptance among physicists. Supersymmetry, a proposed extension of the standard model, would cancel some vacuum energy through paired contributions from matter and antimatter partners of all known particles. But supersymmetry, in its simplest forms, has not been observed at particle accelerators, and versions that remain consistent with experiments do not fully solve the cosmological constant problem. Other proposals face similar difficulties, working in some respects but failing in others. The interpretation of virtual particles remains debated among physicists, with some arguing that they are real physical entities, and others arguing that they are merely calculational tools, mathematical conveniences that help us compute correct answers without necessarily representing physical reality. The debate matters because the vacuum energy comes from summing contributions from virtual particles. And if these particles are not physically real in some sense, the calculation might not represent physical reality either. The philosophical question connects to the technical problem, the relationship between quantum mechanics and gravity. Two of the most successful theories in physics remains imperfectly understood, and this imperfect understanding may be at the heart of the cosmological constant problem. Quantum mechanics describes the very small with extraordinary precision, while general relativity describes gravity and the very large with equal precision. But combining them into a single consistent framework has proved enormously difficult, and the vacuum energy problem may be a symptom of this deeper challenge. A complete theory of quantum gravity might resolve the discrepancy. Laboratory experiments continue to probe the properties of the vacuum, measuring the Casimir effect and related phenomena with ever-increasing precision to test theoretical predictions. Each improvement in precision tests the theory more stringently, potentially revealing discrepancies that might point toward new physics. So far, the measurements agree with theory to the limits of experimental precision, confirming the basic framework while leaving the cosmological puzzle unsolved. The experiments provide data that any eventual solution must accommodate. Theoretical approaches to the vacuum energy problem span a wide range, from modifications of fundamental physics to statistical and anthropic arguments about why we observe the particular value we see. Some approaches try to explain why vacuum energy should be small, proposing mechanisms that naturally cancel or suppress it. Others accept that vacuum energy might vary across a multiverse and argue that we observe a small value because only small values allow observers to exist. The diversity of approaches reflects both the difficulty of the problem and the creativity of physicists trying to solve it. The question of whether vacuum fluctuations are physically real or merely mathematical constructs touches on deep issues in the philosophy of physics. The fluctuations cannot be observed directly, only through their effects on other things, which some argue means they are not real in the same way that persistent particles are real. Others counter that anything with measurable effects is real enough for physics, which concerns itself with what is measurable rather than with metaphysical questions about underlying reality. The debate continues without resolution. The search for quantum gravity, a theory that would unify quantum mechanics with general relativity, might eventually explain the vacuum energy puzzle by revealing how gravity responds to quantum fluctuations. String theory, loop quantum gravity, and other approaches to quantum gravity all propose different frameworks for this unification, and each has implications for how vacuum energy might behave. None has yet succeeded in fully solving the problem, but progress continues, and future developments might bring breakthrough understanding. The vacuum energy problem illustrates how successful physics can be in some respects, while struggling in others, predicting with remarkable precision the effects of vacuum fluctuations on atoms, while failing to understand how that same energy affects the cosmos. The discrepancy is humbling, a reminder that our understanding remains incomplete despite many successes. The universe knows secrets we have not yet discovered, and the vacuum energy problem points toward at least one of those secrets. New observations of the cosmos might provide clues that help resolve the vacuum energy puzzle, revealing properties of dark energy that constrain theoretical approaches. The nature of dark energy remains uncertain. Whether it is truly constant, as vacuum energy would be, or whether it varies in time or space, as some alternative theories propose. Better measurements of cosmic expansion, galaxy clustering, and other cosmological observables might distinguish between possibilities and guide theoretical development. The answers may come from the sky. The humility that physics teaches includes acknowledging what remains unknown, alongside celebrating what has been discovered. The vacuum energy problem reminds us that even well-established theories have limits, that the universe is stranger than we have yet fully understood. The recognition is not discouraging but motivating, pointing toward future discoveries that will extend our understanding into territory currently marked as unknown. The problem is an invitation to future physicists. The mysteries that remain should not obscure what we have learned. That empty space is not empty, that the vacuum contains energy and activity, that the universe is richer than simple emptiness would allow. The space around us right now, the air filling whatever room or outdoor area we occupy, seems empty enough from everyday perspective, transparent and invisible, and apparently containing nothing at all. But physics has revealed that this apparent emptiness is a kind of fullness, a quiet activity, humming along at scales we cannot directly perceive, energy fluctuating and particles flickering in and out faster than any instrument could catch. The revelation came from careful thought and careful experiment, from mathematics that pointed towards strange conclusions and observations that confirmed them. We learned that nothing contains something after all. The energy of empty space exists throughout the universe, not just in the spaces we might notice or think about, but in every cubic centimeter of cosmic volume. The darkness between galaxies contains this energy. The space between stars within galaxies contains it. The room you occupy contains it. The spaces between atoms in your body contain it. The universality is complete and democratic, applying everywhere without exception, a foundation layer of reality beneath everything that appears more obviously real. We are surrounded by and permeated with this subtle activity. The discovery emerged from the development of quantum mechanics in the early 20th century, from the uncertainty principle and quantum field theory and the mathematical frameworks that physicists built to describe reality at the smallest scales. The discovery was not obvious or expected, but emerged from following the mathematics where it led, even when it led to conclusions that seemed to violate common sense. The mathematics insisted that empty space contained activity, and experiments confirmed what mathematics predicted. The strangeness was real. The effects of vacuum fluctuations touch everything from atoms to light to the cosmos itself, influencing properties that can be measured and compared to theoretical predictions. The Lamb shift in hydrogen atoms, the electron's magnetic moment, the Casimir force between close surfaces. All of these confirm that the vacuum is active and that including its effects brings theory into agreement with observation. The confirmation is extensive and precise, leaving little room for doubt that the fluctuations are genuine features of physical reality. The emptiness pushes, shifts, and influences. The connection between vacuum energy and the accelerating expansion of the universe remains tantalizing but incomplete. The huge discrepancy between calculation and observation, one of the great unsolved problems in physics. The connection suggests that what happens at the smallest scales influences what happens at the largest scales, that the quantum and the cosmic are linked through the energy of empty space. Whether this connection will be confirmed and understood remains to be seen, a challenge awaiting future physicists and future discoveries. The philosophical implications of the discovery invite contemplation, suggesting that what we casually call nothing is actually something, that emptiness has properties and behaviors rather than being the mere absence of everything. The questions that arise touch on the nature of existence itself, on what it means for something to be real, on the relationship between the mathematics that describes reality and the reality it describes. These questions will continue to be explored long after specific technical problems are solved. The discovery does not ask anything of us in a practical sense, does not require action or response, does not change how we move through rooms or look at the sky. The emptiness will continue its activity whether or not we think about it. The fluctuations occurring regardless of human awareness or attention. The universe proceeds according to its nature, and we have simply learned something about that nature that we did not know before. The knowledge is a gift, freely given by the universe to those who ask the right questions. The patience required to understand the vacuum mirrors the patience that the vacuum itself seems to embody, quietly active, moment after moment, epoch after epoch, throughout all of cosmic history. The fluctuations were occurring when the universe was young and hot. They continue now in the mature cosmos we observe, and they will continue into the far future, long after the specific circumstances we inhabit have changed. The vacuum is patient and persistent, a constant presence underlying the changing world of matter and events. The wonder of learning about the vacuum lies not in dramatic implications, but in quiet appreciation of a truth that was hidden until careful investigation revealed it. We do not see the fluctuations, cannot feel the energy, have no direct experience of what physics describes as filling all of space. But knowing it exists changes how we might think about emptiness, about space, about what lies beneath the surface of things. The universe is richer than it appears, more interesting than naive observation would suggest. The night continues, the space around us continues, the vacuum fluctuations continue, all of it proceeding as it has always proceeded, whether or not we attend to it. The energy of empty space asks nothing of our attention, requires no acknowledgement, simply exists as part of how reality works at the most fundamental level. We have learned something true about the nature of things, and the truth will remain true whether we remember it or forget it. The emptiness that is not empty surrounds us now as it always has, and will continue surrounding us as we drift towards sleep, a quiet fullness beneath the apparent stillness of the night. The universe is strange and wonderful, and one of its strangenesses is that nothing contains something, that the void is full, that space itself participates in the activity of existing. The knowledge is peaceful to hold, a small piece of the cosmic story that we can carry with us into rest.